Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, welcome everybody. It's a great pleasure to have David Woodruff from IBM Research here. David works on streaming algorithms, sketching algorithms, low dimension embeddings, and related topics. He did some great work in this area and got several Best Paper Awards at top CS conferences. He was also recently awarded a very prestigious Pressburger Award. And today, David will tell us about some of his works that involve streaming algorithms and sketching.
Okay, so thanks for inviting me to give this talk. The title of the talk, Turnstile Streaming Algorithms Might As Well Be Linear Sketches. So the goal of this talk is to try to characterize all optimal algorithms in a certain natural, for a certain natural streaming model. This is joint work with Yi Li and Hui Nguyen. So the Turnstile streaming model, which is a well-studied streaming model, is the following. So you're given an underlying n-dimensional vector x, which is initialized to all zeros. And what happens is you see a long stream of additive updates to the coordinates of x. In the form that x goes to x plus ei or x goes to x minus ei for standard unit vectors ei. So you can think of this as items coming and going in a stream, where the ith coordinate of x corresponds to the number of times item I is there. At the end of the stream, you're promised that this underlying vector x is inside of some bounded integer box. So all the coordinates of x are between minus m and m for some parameter m, which for the sake of this talk, let's think of m as being polynomial in n. What you would like to do is to compute a function or an approximation to a function f of x with high probability. So usually for efficiency reasons, you want to you need a randomized approximation algorithm. And the goal is to use as little space in bits as possible to do this. So the memory required of the algorithm is one of the main goals. So of course you could just store x, but you want to do with much better space complexity. Okay, so this is the Turnstile streaming model. What are some example functions f that people have tried to approximate in this model? Okay, so one example, one well-studied problem is are the LP norms. Typically what you want for these norms is to achieve relative error, right? You want z to be within 1 plus or minus epsilon of the p norm, or equivalently for approximation, the pth power of the p norm of x. And this is a well-studied problem with many applications. Of course, the Euclidean norm has applications to geometric and linear algebraic streaming algorithms. The one norm has applications to measuring distance between distributions presented in a stream, which is useful for things like network monitoring, etc. Okay, so these are some problems. Now let me give you a flavor of algorithms in the streaming model. And you don't have to really understand why the algorithms work so well. I just want to give you sort of structurally what do these algorithms look like. And I want to try to abstract some generic features from these algorithms and prove a characterization. So what is an algorithm for the Euclidean norm in a stream? Okay, so the algorithm is quite simple. So let the parameter r be 1 over epsilon squared. What you do is you choose a random r by n matrix A of IID sign random variables. So each is plus or minus 1, independently with probability 1/2. So this is a very wide fat matrix. And what you do is you maintain a times x in the stream, which is easy to maintain under additive updates to the coordinates of x, because I just add the corresponding column to the sketch. And note that ax, the dimension of this vector is only r, which is 1 over epsilon squared. So we're doing quite well. And after processing the stream, all you do is you output the Euclidean norm of A times x, rescaled by square root r. And the proof that this works is basically this, that these bounds work. This is, it's an immediate consequence of the Johnson-Lindenstrass lemma. So one thing is regarding this sign matrix, you can actually generate the entries from a four-wise independent family. So that can be stored succinctly. So this is a simple algorithm, and I just want you to see the sort of the structure of this algorithm. Because for the one norm, there's a very similar algorithm due to indic. So again, set the parameter r to be 1 over epsilon squared. You're going to do a very similar thing. This time you choose an r by n matrix A of IID Cauchy random variables. So these come from the Cauchy distribution. It's a continuous distribution. Doesn't matter so much what it is. I'll just describe the property we need of it. But all you do is, again, you maintain A times x in the stream, which is much lower dimensional. And at the end of the stream, this time the estimator is a little bit different. You output the median of the absolute values of the coordinates of A times x. And you can show that this works. So, and basically the proof, it just uses, the only property of the Cauchy distribution that it uses is the one stability property. So basically if C1 and C2 are independent Cauchy random variables, then if I look at A times C1 plus B times C2, where A and B are scalars, this is equal in distribution to another Cauchy random variable C3 times absolute value of A plus absolute value of B. So basically each of these AXIs is just the one norm of x times a Cauchy random variable. And you can show that this estimator works. Again, it's low space. You can show that these can be drawn from a family of random variables which has limited independence, so A can be stored succinctly. So both of these algorithms have a very similar form. And the goal of this work is to try to abstract that form. So what are some generic features of these algorithms for norms? So what you do is before the stream begins, you choose a random matrix A independent of x. Then you maintain A times x in the stream, which we said was easy to do. And at the end of the stream, you output some function of A times x. Maybe the Euclidean norm or the median in those two examples. And a natural question that one sort of can't help to ask is, does the optimal algorithm for approximating any function in the Turnstile model have this form? So not necessarily a norm, just any function of the underlying vector x that's being updated. And I should note that actually for all problems studied in this model, all known algorithms do have this form, can be cast into this framework. Yeah?
Can any f be approximated in this framework?
I can always just store x, and then I can compute any function. So it depends like how much space you ask for. So different f require different amounts of space. I should note that some functions may be quite weird, and it's not clear that intuitively the best approximation is to maintain a linear sketch. For instance, these pointer chasing type functions where I read the first coordinate of x, which has some value, which indexes into another, which chooses another coordinate, and I output that value of that other coordinate. Why should the best algorithm for that be a linear sketch? Okay, so what we show is that actually the answer is yes, up to a factor of log n. The optimal space algorithm does have the above form. And let me qualify that by formally stating the theorem, because there are some caveats. So the theorem is as follows. So for computing a relation f for an underlying vector x, which is promised at the end of the stream to be inside of this bounded integer box, then there is a correct with high probability algorithm which does the following. So before the stream begins, it samples an integer matrix A uniformly from a small number of matrices, n log m, which are hardwired. So there's some amount of non-uniformity here. In general, we don't know how to represent these matrices in small space. But the matrices, they have poly-n bounded integer entries. And then what we do is we maintain a times x in the stream, and then we output a function of a times x. And what we show is that the logarithm of the number of states of ax, so what a state is as I range over x inside of this integer box, I get potentially different images a times x. If I look at the logarithm of the number of distinct images I get, together with the amount of space needed to store the randomness, which is actually just log n bits, because the randomness is only used to choose one of these hardwired matrices uniformly at random, then this is optimal up to a log n factor in this space. OK, so before I get into some of the details of this theorem, in particular, one thing that we need to go over is the non-uniformity. Let me just state an application where the non-uniformity doesn't matter. OK, so the application, one consequence of this theorem is to proving lower bounds for data stream algorithms. So the standard way of proving lower bounds is via communication complexity. And most often, people look at two-player communication complexity. So what you have are these two players, Alice and Bob, with inputs A and B, say n-bit strings, to some communication problem. What they do is from their inputs, they locally create streams S of A and S of B in some arbitrary way. And the lower bound technique is the following. Basically, that there's some streaming algorithm, alg. Alice runs it on her stream S of A and transmits the state of that algorithm to Bob. Then Bob continues the execution of the algorithm on his generated stream S of B. And at the end, what you'll have is that the algorithm will have been run on the concatenation of these two streams. And if Bob can solve some problem, G of AB, these inputs to the communication game, then the space complexity of the algorithm, the streaming algorithm, must be at least the one-way communication complexity of solving this problem G. Right? Now, I'm not going to formally define communication complexity, but basically one-way communication complexity is sort of the, so it's one way. Alice sends a single message to Bob. And what we look at is sort of the best protocol with the minimum message length maximized over all inputs. And so in this case, what happens is, the message that Alice is sending is the state of the algorithm. And this is why we get this lower bound. And so one-way communication complexity is often easier to prove, often but not always, easier to prove communication lower bounds than for general communication complexity when both players can interact. So what our main theorem implies here is that actually we can look at an even more restrictive communication model. Instead of one-way communication complexity, we can do the following. So again, they do the same thing of creating these local streams S of A and S of B. And if the players can solve this problem G of AB, then the space complexity of the algorithm must be at least the simultaneous communication complexity of G. And let me describe what that is. That's an even more restrictive communication model. And so it allows for proving lower bounds in a new way. It gives an avenue for easier proofs. And so what is the simultaneous communication complexity of G? So in that model, you have these two players. And instead of Alice sending a message to Bob, what happens is they share some public coin. And what they do is they locally create a message based on the public coin and their inputs. And they send this message to the referee. So there's a third player called the referee who sees these two messages. And then he decides the output based on those messages. So it's more restrictive because, of course, in the one-way model, Bob could simulate the behavior of the referee. But our main theorem implies that it suffices to look at this. And it's not obvious, how to reduce a streaming algorithm. It's not obvious why this lower bounds in this model give lower bounds for streaming algorithms. But what our main theorem says is that the optimal streaming algorithm up to a log n factor is a linear sketch. So basically, the way this proof works is that the players use the public coin, some shared randomness, to choose a common sketching matrix. So as we said, there are, our main theorem implies there are a small number of sketching matrices, order n log m. So if you sample one uniformly at random, that it works for your input with high probability. So they choose a sketching matrix from the public coin. Alice applies that sketching matrix to her stream. Bob applies that sketching matrix to his stream. And they send these sketches to the referee. And because of the linearity, the referee can add the two sketches. So A times S of A plus A times S of B. And therefore, that's how you do the simulation in this case, using our theorem. And so this has some consequences. We're able to prove some new lower bounds using this framework for estimating p norms. I should note, if you're familiar with things like multiplayer set disjointness, a lot of proofs become easier in this model than in the one-way communication model. For instance, there were lower bounds for multiplayer set disjointness, which were first in the simultaneous communication model, and then later people were able to get it for the one-way model. OK, and note that the non-uniformity doesn't really matter here, right? Because communication complexity, it doesn't really, I mean, we're not looking at players' space or time complexities. And so basically, they can, there's a constructive procedure to generating those matrices, small number of matrices. But it's not efficient, but it doesn't matter for proving communication lower bounds. Any questions on that? OK, so yeah, so that's one application. So let me describe the non-uniformity now in more detail. So as I said, what you do is you sample this integer matrix A uniformly from a small number of hardwired matrices with poly n integer bounded entries. And not only is the non-uniformity there, so there's non-uniformity in that we don't know how to store these matrices A in low space, but actually we don't even know how to store the output function of the streaming algorithm in low space. So this needs to be hardwired as well. So what that means is that for each A times X, what I do is in my non-uniformity, I hardwire the output that I should produce if I have A times X. So note that this doesn't cause any sort of indexing problems into the non-uniformity, because if I'm storing A times X already, then that sort of indexes into what my answer should be in the non-uniformity. Also, I'm storing the identity of A with these log n random bits. So I can index into this non-uniformity. If you don't like non-uniformity, you can alternatively allow the algorithm to use more space to process a stream update, provided it only retains A times X and its randomness after processing each update. So basically what I'm saying is that there is a constructive procedure for which what you can do is during each stream update, you can run this procedure and you can regenerate this matrix A. You can generate these n log m possible matrices. You can use your randomness to choose the one that you've been using. And if you're updating one to the ith coordinate, you can add the ith coordinate of A to your sketch, A times X. And then you can throw away all that additional space that you use to generate these matrices A. So basically, in between stream updates, all you do is maintain A times X in the randomness. But when processing a stream update, you can use a lot more space. So this could have applications in sort of multiplayer communication, where the communication is what matters. And locally, if people have updates, they can use more space. Yeah?
Do you count the states already in these hardwired matrices? That's also a part of the state you have to...
No, so the algorithm is non-uniform. So it has these hardwired matrices. And there are n of them, right? So that would already be n bits of space. So the non-uniformity is not counted towards the space. And it's also like for these applications like communication, it doesn't go into the communication because, as I said, like non-uniformity is not important for communication lower bounds because the players use the public coin to choose one of these matrices. They just have to agree upon one of them. And yeah, does that make sense? Okay.
So is your graph is an p/poly or?
No, so you mean how hard is it to generate these matrices A? Yeah, so it's a very it takes a lot of time to generate these matrices A. Not even in polynomial time that I know of.
You can sort of, they take polynomial time. Sorry, they take polynomial space. So you can
yeah. I mean, in p/poly, yeah.
This step is it sort of polynomial? Can you store it in polynomial? This output, the second population.
Oh, for each state. No. So because basically what you're going to get is for every a times x, you have an output, and just sort of the number of outputs could be super polynomial. It depends on the number of outputs is basically exponential in your space bound. So.
Oh, I see. Because you are proving only the communication lower bound. So if you pre-store everybody, like both Alice and Bob pre-store like a bunch of matrices.
Yeah.
Then this doesn't count.
Yeah, exactly. So it doesn't play any role for proving lower bounds.
Lower bound, okay.
For upper bounds, I mean, in general, we don't know if it's possible to represent these matrices A in low space, and it's probably not because I'm claiming this for an arbitrary functions. So. Okay. So another comment on the model is the following. So for each random seed of the algorithm becomes a deterministic automaton with a finite number of states. So I'll describe more what that means in this context in a few slides. But let me say the following, so that the main theorem, it only requires correctness under the promise that x is inside of this bounded integer box at the end of the stream. So you're given this promise that x undergoes all these updates to its coordinates, and then at the end it's inside of some integer box. So while processing the stream, it may be the case that some of the coordinates may be outside of this box. Right? You have some long stream. Who knows what's happening as you go. And one restriction is the algorithm is not allowed to abort if the coordinates leave this box at some intermediate point in the stream. So basically, if one of the coordinates leaves this box, but later at the end of the stream it's inside of the box, then the algorithm must still be correct. So this is sort of like so there's a feature here, which is that, let me just say this. So what we're going to do is we're going to take the optimal algorithm. We're going to fix its randomness, and we get an automaton. And what we're going to do is we're going to count the number of states as x varies over this box. So it's going to be some automaton with lots of states. But some of these states might not correspond to any x inside of this box. The only x that might reach this state in the automaton might be from some x which is outside of the box. We're not going to charge that algorithm space for those states. And this is a feature in the sense that what we're going to do from the automaton is produce a linear sketch. And the linear sketch, the number of states of the linear sketch is about the same as the number of states of the optimal algorithm when measured in this way. So basically, it's now if we produce a linear sketch, what we're doing is we're counting the number of images a times x as x ranges over this box, instead of a times x for all possible x with large coordinates. But we can always take a times x mod each of the coordinates poly n. And if we do that, then that means like the total number of states that you would ever see is actually the same as the number of states, proportional to the number of states when x varies in this box. And the algorithm is correct at the end of the stream because ax mod poly n will equal ax given this condition. So it's just a technical, well, it's a condition. So, okay, so Another comment is on the log n factor loss. So as I said, like what we do is we take an arbitrary algorithm and we show without loss of generality it can be a linear sketch, but the linear sketch might have a log n factor more in space than the optimal algorithm. Now this log n factor loss is actually necessary if we're producing a linear sketch over the integers. One way to see that is just to consider the function f of x equals x1 mod 2. So what is the optimal algorithm for this function? Well, I just maintain one bit, which is the parity of the first coordinate. So it has two states. But if I'm trying to compute this with a linear sketch, if I look at a times E1, the standard unit vector with the 1 in the first position, zeros elsewhere, then that should be non-zero if the algorithm is correct. And then if I scale E1 by 2, I get a new state. If I scale it by 3, I get a new state, etc. So if I scale it n times, I get n states. Right? So basically, I went from 2 states to n states. So there is a log n factor loss that is necessary if you want a linear sketch over the integers. That makes sense?
Wait, what is it? N and not m?
Yeah, so m I'm saying is poly n. So it's a log m, yeah. Okay. All right. Now before describing how this characterization works, let me just mention some related work of Ganguly. So what Ganguly did is he tried to characterize all optimal algorithms, but for a specific problem called the heavy hitters problem in data streams. And he also only looked at deterministic algorithms. But nevertheless, some of the notions he introduced are useful in our characterization theorems. So, okay. So in the remainder of the talk, I'll try to give an overview of how the proof works. So basically what's going to happen is you start with the optimal algorithm. For each fixing of its randomness, you're going to get some automaton. And what we're going to try to do is pretty up that automaton. We're going to try to make it have some special properties, which I'll call being path independent. And once we reduce the automaton to a path independent automaton, then it's not so hard to reduce that to a linear sketch. And so that's sort of how the proof will work. Okay, so yeah, what is an automaton, first of all, in this context? So yeah, we have some streaming algorithm. For each fixed randomness, it looks like the following. So we have some states, and we have a transition function. So we start in this state where the underlying vector x is initialized to all zeros. And we see updates. So suppose we see the update, add 1 to the first coordinate, then we might go to this state, etc. So subtract 1 from the first coordinate, I go to this state. So this is just a generic automaton. And what I said is we'd like to get some control over what this automaton looks like. So a property that we want is the following. We would like that the streaming algorithm, the state that it's in, it only depends on what the current value of this underlying vector x is. Right? So this vector x is evolving. We don't want it sort of to depend how it got there. So note that this particular automaton does not have this property, because if I start in this state and my vector x is initialized to all zeros, if I add 1 to the first coordinate and then subtract 1 from the first coordinate, the all zeros vector also goes to this state. So this is something we'd like to avoid. Okay. Yeah, so 0 to the n is in 2 different states. So this motivates the definition of a path-independent automaton, which is for each underlying vector x, there's a unique state for which in the automaton which contains x. Now note that most states should contain many vectors x if you want a small amount of space. So if you have this path-independent property, you can think of this underlying automaton as being an undirected connected graph in the following sense, that if I'm in some state and I add 1 to some coordinate and go to some other state, and I subtract 1, then I should go back to the state I started with. I mean, that's what it means to be path independent. And so in some sense, it's undirected, that I have parallel directed edges everywhere. So a natural goal is, for each fixing of the randomness of the algorithm, we get an automaton, and can we modify it to make it path independent without increasing the number of states, and while preserving the overall correctness of the algorithm. Okay. Yeah, so this would rule out algorithms that, for example, remember the last 5 stream updates and try to do something with them. Okay, so the strategy is as follows. We're going to introduce the notion of a frequency vector of a stream. So for a stream sigma, let frequency of sigma be an integer vector, which is the net update to each coordinate in the stream sigma. So sigma is a long list of updates, and for each coordinate I look at all the positive updates and I subtract all the negative updates, and I get my net update. That's my frequency of sigma. And the idea is the following, that if I'm in a state S and I update by a stream sigma which has 0 frequency, then, and I get to some new state, then the answer in the new state ought to be similar to the answer in the old state. Right? If the algorithm is typically correct, then this should, on most inputs, according to some distribution, then this should be what happens. And so the idea is maybe we can collapse all states S and S prime in the automaton, for which, with some abusive notation, I start at state S, and I add or execute the stream of updates in sigma and get to S prime. And sigma has 0 frequency. So this is intuitively making things path independent, right? Okay, so the issue is how to formally define the new states, the states of the new automaton, the transition function, and the output function. And to guarantee that overall we have a correct algorithm. Okay. So we're going to introduce the notion of a 0 frequency graph, which is a directed multigraph G. The nodes of this graph are the states of the old automaton for a fixed randomness. And what we're going to do is we're going to draw an arc from state S to state T if there's a stream sigma for which if I start at S and I add sigma and I get to T, and sigma has 0 frequency, and sigma has 0 frequency. So I connect all, so it's a multigraph. So what's going to happen is I fix some a priori length bound on the streams. It's going to be a super large length bound, but finite. And what I'm going to do is for each stream in that length bound, which has 0 frequency, I'm going to draw an arc from S to T if it connects S to T. Okay, so it is a multigraph, right? I could have many arcs between S and T.
Yeah, sorry, I forgot what's the frequency. What is the frequency?
Oh, okay. Yeah, the frequency of a stream sigma is I look at all the, it's an n-dimensional integer vector, and the ith coordinate is the sum of all the positive updates to the ith coordinate in that stream minus the sum of all the negative updates. Right? So being 0 frequency means I added 1 to each coordinate I the same number of times I subtracted 1. But the ordering is completely arbitrary.
So they should cancel out, basically. It's like no update at all, right?
Yeah, so basically all the updates, the net update in each coordinate is 0. Okay, so what we're going to do in this zero frequency graph is define a terminal equivalence class. Now what this is it's just a strongly connected component in this directed multigraph with the additional property that there's no way you can escape. So there's no outgoing edge of this strongly connected component. Okay. And basically an observation is that suppose I'm in this zero frequency graph G, and I take some arbitrary walk along the edges. Then the observation is that eventually my walk lands in a terminal equivalence class for a long enough walk. And just to remind you that what is a walk in G? So you're not walking along the transition function. What you're doing is a walk in G consists of a long sequence of zero frequency streams, right? And just all concatenated together, this long sequence. Okay. So what we're going to do is, for the old automaton, we're going to look at its zero frequency graph, and we're going to define the states of the new automaton to be the terminal equivalence classes of the old automaton. Okay. Yeah.
Can you just explain why this is so? Isn't there a natural underlying group structure, and then you can just divide by the commutator?
So this is an arbitrary automaton. So.
Okay, but yeah, sure, but for our setting, isn't there always a group structure because the updates are just from updates of X and something?
Why is there a group structure? The order, I mean,
Okay.
the order of updates matters, right? So
Yeah, of course, not a billion, but a group structure. It's clear.
That's, I think, one of the problems. That you can, if you apply sort of this zero frequency stream, right, you may land somewhere else.
Yeah, this just means the group is not a billion, but I don't see why there is no underlying group. Okay.
would there be?
What's the underlying group?
Just then all this process.
Can you assume that this graph, this multi-graph is sort of undirected? Then
Can assume that it's undirected.
undirected. Yeah, if you apply sort of one stream of frequency 0, and if you apply sort of reverse stream, you go from there.
No, you can't assume that. I mean, that's kind of what you sort of want to prove, right? I mean,
That's not the only thing you want to prove, right?
you want to prove something stronger than that, but that would be implied by the stronger.
But that part is actually
No, so
because you can always
I guess I'm
assume
missing
that,
something.
or whatever, that's the question. Can you always assume that if you have, plus E1 age, then minus goes back?
no, you can't. I mean,
If you just change the, if you just pick your
unwind this.
instance and manually kind of change that, want that,
all these conditions.
but how do you? Oh, you want to change the algorithm, change the graph so that it has that.
automaton, right? If I change it,
But how do I do that in a global way? That I mean, and to preserve correctness. I mean, this is sort of what this proof is going to give.
local changes are easier, but okay, probably first.
Or maybe ask again after this proof.
On all the
It's a semi-group.
Okay, well,
Oh, okay. Oh, no problem. Okay, so it's clear what the states of the new automaton are, right? Terminal equivalence classes of the old. What is the Oh, sorry, yeah.
Go back. So I didn't quite understand. What did you mean, like a walk in G eventually reaches?
Which is a terminal equivalence class?
So it doesn't. I mean, it doesn't have to, right? It could just kind of.
No, because like if you're at some node and you look at like what it can reach, and one of the things that it can reach, if all the things it can reach can go back to that node, then it would be strongly connected. But if there's something it can't reach, then if I sort of take a step from that node, then either I can't go back to that original node, or that thing that original node can't reach can't reach the new node, because otherwise, right? So basically, you can peel off vertices and argue that eventually you need to land inside of one of these.
But eventually, you mean worst case on all paths, or when you?
I mean with a long enough walk.
So you're doing a random.
But in any directed
Time
graph, right?
probability?
No, but it's always right. In any, it doesn't matter what the.
Oh, it's a finite graph as a function.
Graph you eventually will
So it's
end up
not going
in
to
a,
repeat vertices.
connected component, right?
The number of
What the
vertices.
graph is. This may be one vertex as well, but.
The number of vertices doesn't depend on the number of updates, right? It's a function.
Only connected component. I mean, you may always have edges out to another communicating class which you don't use. Do you mean typical?
No, because the number of vertices is a function of n, right? So like, I mean, I fix my underlying graph, which is some function of n, and then I take these really long walks. And so basically, I will eventually land in this terminal equivalence class. It's not like I'm getting new vertices.
What I think where
yeah.
some of us are missing is just the picture of, suppose I have some cycle that I can, directed cycle that can go around. And there are also edges going out from that to some terminal states, but I just don't use them. And I keep walking along this directed cycle.
Oh, you're saying, yeah, okay. What do I mean by walk, right? Is that the question? Yeah. So I mean, one thing I can say is a random walk. We'll eventually get there with high probability. Yeah.
So that's what you meant, that a typical walk? You didn't do all paths?
Yeah, so I mean, it suffices for a random walk to have this property, but you'll see how this is used in the proof. Like, basically, I'm saying.
I understand, but
yeah.
Is that what you meant before, a random walk, or was that what was the?
What are properties? What properties do you need of this in the proof?
I guess you just take the definition of a terminal equivalence class. You don't need anything else.
Yeah.
At the
I see.
moment.
There is some walk which will land there. In fact, that's all we need, actually, that some walk will land in a terminal equivalence class. I mean, so basically, I start at some node, and there's some walk to a terminal equivalence class. OK, you'll see like exactly what is needed on the next slide. And it should be more clear. So, OK, so in fact, you'll see it here. So we need to find a new transition function. OK, so suppose I'm inside of some terminal equivalence class, C. And I'm given an update, EI. I need to define a transition function. What do? So I let V in C be an arbitrary node. This is a state of the old automaton. Right? The states of the zero frequency graph, the vertices of the zero frequency graph are the states of the old automaton. Now what I do is I compute the new state, V plus EI, using the old transition function. Right? So the old the old automaton comes with a transition function, which says that I'm in some state V, and I add EI, I go to some new state. So this is a state is also a node in the zero frequency graph. And so what I do is I take a walk from V plus EI, and this is getting to your question, to a terminal equivalence class C prime. Yeah.
Isn't every node part of some terminal equivalence class?
No,
It's an equivalence
no,
class.
because I could sort of start at a node and walk away from it and never go back, right? I mean,
No, but your equivalence classes, every time you have a zero frequency update, you go back to that class.
yeah, but I mean, I could start at some node which is not in a terminal equivalence class, and I can execute a bunch of updates. I get to some terminal equivalence class. In there, if I update with zero frequency streams, I'll stay inside of it. But why will I ever get back to my original?
I'm probably.
Oh, okay.
So basically, your terminal, your relation that you're defining, that you're connecting one node to another, if it's a zero frequency update, it's an equivalence relation. So there is an equivalence partition, and
No.
No, that's really the issue.
I mean, it's sort of what we're trying to prove in some sense. But like there could be.
It's not an. It's not symmetric. So it's a directed graph. So this is the.
oh, okay, it's not symmetric. Okay, so
Yeah, I mean, ultimately, we want a statement of that form. Yeah.
But C prime is like it's not uniquely defined, right? The way you define it. Right?
So that's a great question. It is uniquely defined, and I'll show why that is. So that's why it doesn't actually matter. Like you just need a walk that gets you to a terminal equivalence class C prime. Yeah. That's your answer. What?
You apply the same update over and over, right? Or sorry.
So what I'm doing is I'm saying, how do we define the transition function? I see EI, I choose an arbitrary node, and I take an arbitrary walk until I get to a terminal equivalence class. And the claim is that it doesn't depend on the choice of node that I chose in the terminal equivalence class. And actually, there's only one terminal equivalence class reachable from any walk. And this second property, it's crucial that I started in a terminal equivalence class. So you'll see the proof now pictorially why it's unique. OK, so yeah, what's going on here? So I'm in some terminal equivalence class, some state of the new automaton. And I had multiple choices, say U and V, of how to do my update, right? Suppose I chose U, and I did the update EI according to the old automaton. And I got to this state. And now what I did is a zero frequency stream walk. So it's a walk in the zero frequency graph. And eventually I said, so there's a walk which gets me to a terminal equivalence class. And suppose if I were to choose V, a different vertex in the original terminal equivalence class, and do the same thing, I would get to a different terminal equivalence class. Now, I claim that these two terminal equivalence classes are the same. Yeah.
Maybe I should ask it in the end, but like, can't you create a graph, like can't you discretize all your update and create a directed graph where if you take that update, you go there, and if you subtract that update, you go back?
Sorry, what do you mean by discretize the graph?
So discretize all the updates into edges. So like if you can have delta 1 as your discrete, the smallest possible discrete update.
Oh, let's just say all the updates are 1 or minus 1.
1 or minus 1. So you can have like, if you take a 1, you go there. If you take a minus 1, you go back. And that way you will...
Well, I mean, that's what we're trying to prove, that we can take this automaton and get it into that form. I mean, so that is implied by being a path-independent automaton. If I'm in some state and I add E1 and I subtract E1, I should go back to the same state.
Maybe in view of time, we'll let him
Yeah,
finish.
sure.
But I mean, I don't see how you
Important
could...
point that in the original model, it's you don't like just return to the same state just because you add one and then subtract one.
Yeah, I mean...
The whole point is it's time dependent. So the whole point is to kind of prove that property.
Yeah. I mean, we're trying to show the automaton has what you said. And I don't see how to do it by sort of locally adjusting things, if that is what your question is.
+1, -1.
OK, so why are these two terminal equivalence classes actually the same? So suppose that I started at U, and I executed this path and got to a terminal equivalence class, and I got to some node W. Then what I could do is from W, suppose I have the update minus EI. Then let's look at this path. It's actually a zero frequency path because I start at U, I add EI, I take a long sequence of zero frequency streams, and then I subtract EI. So the net update is actually 0. So what that means is that W, when I subtract EI, I must return to some node X inside of my terminal equivalence class. Right? Because it's a zero frequency update stream, and there's no outgoing edge. I can't escape this terminal equivalence class. Now also, this terminal equivalence class is connected. So there's a zero frequency stream path from X to this other node V that we said we could have used instead. And now we said from V, suppose if I were to add EI and get to some state and do a zero frequency walk, I got to some other terminal equivalence class. But then these two terminal equivalence classes are actually connected by a zero frequency path, right? From W, I do minus EI, I do a zero frequency path, I do plus EI, and a zero frequency path. But that means they need to be the same terminal equivalence class because you can't escape. I mean, that's the definition. OK, so that actually shows that it doesn't matter if you chose U or V to do the update based on. And it also doesn't, you can show that you can only reach a unique terminal equivalence class from a node for the same reason. Okay, yeah, so good. Okay, so we defined the transition function. Now we want to define the output function of this new automaton. So what are we going to do? So in each terminal equivalence class C, we're going to do the following. We're going to sample a node U from the stationary distribution from a random walk inside of this terminal equivalence class. Okay, so it's strongly connected. We're going to add self-loops with some positive probability to each of the nodes. So the stationary distribution exists. These self-loops, they correspond to empty streams. And what we're going to do is the output of the new automaton on this terminal equivalence class C is going to be the output of the old automaton on this vertex U that you sampled this way. Okay, so what doesn't work, or at least what I don't know how to prove works, is if you were to instead choose an arbitrary vertex in this terminal equivalence class and output with that outputs. I don't know how to prove that works. Intuitively, what's going to happen is you're going to want some distributional correctness. And some of these arbitrary nodes might just be bad nodes, give the wrong answer. You could try to choose a random node, but what does random really mean? Like, are you really at a uniformly random node or not? Like, maybe that's also a bad node. So I'll explain why this choice works on the next slide. We also need to choose a starting vertex of the new automaton. What we do is we take the starting vertex of the old automaton, and we take a random walk in the zero frequency graph until we get to a terminal equivalence class. Now you could get to multiple terminal equivalence classes from the starting vertex, because the starting vertex need not be in a terminal equivalence class itself. So there's some mixture, some distribution on these terminal equivalence classes that you get. Okay, so we get to some terminal equivalence class, and we let the starting vertex of the new automaton be the terminal equivalence class C that we got to from this random walk. So what we did is we defined the starting vertex, we defined the output of each terminal equivalence class. So we've basically characterized, we said what the new automaton is. We take an old automaton, we get this new automaton. Now, why do we have a correct algorithm? Okay, so what we're going to do is we're going to show that the following. What we're going to do is for every distribution pi on stream, sigma, we're going to show that we have a path-independent automaton which succeeds with high probability over streams drawn from this distribution pi. And then, but from the strong version of the minimax principle, what we're going to do is say that, therefore, we have a randomized algorithm which works for all streams. Okay, so let's see how we can argue that we have a path-independent automaton for an arbitrary distribution pi on streams. And so here is a trick. What we're going to do is, we had our old algorithm, which is a randomized algorithm, so it works for every stream with, for any fixed stream with high probability. So what that means is there's a fixing of its randomness. So I get this deterministic automaton, A old, which is correct on the following distribution, pi prime. Now pi prime is not going to be the same as pi, but it's going to be related to pi. So let me just say what that is. You sample a stream sigma of updates from distribution pi. And you're going to create a new stream sigma prime of the following form. So sigma prime is going to look like a long sequence of zero frequency streams, tau 0, followed by the first stream update, sigma 1, followed by a long sequence of zero streams, tau 1, followed by the second stream update, sigma 2, all the way to the end until you get to sigma r, and then followed by a long sequence of zero frequency streams. So this distribution pi prime is derived from the distribution pi. And the key property is that the output of the new automaton on distribution pi is statistically close to the output of the old automaton on distribution pi prime. And note that the answers are the same, right? If I'm putting a bunch of zero frequency streams for a fixed stream, the underlying frequency vector x, the underlying vector x is the same generated from sigma for sigma prime.
So sigma 1 to sigma is I the sample or?
No. So there's just some arbitrary distribution pi on stream sigma, and these are its updates.
Oh.
Yeah.
Can you say a word on how you randomly choose the zero frequency streams?
So they're just long enough. So each zero frequency stream corresponds to an edge in this zero frequency graph. We choose a long sequence of these things, a long enough sequence, so that, and I'll say it, okay, so that basically a random walk is, what you get is statistically close to the stationary distribution. So let me just say that more. Yeah.
From what distribution on zero frequency streams do you choose?
So basically, these are all zero frequency streams of a long enough length. And you choose enough of them for each of these in-between parts so that, let me just say why the proof is, why it goes through, and then you'll see what's going on. Maybe it's easiest to say it as follows. So what happens is you first execute a long sequence of zero frequency streams, and you end up in some terminal equivalence class. Now, how did we define our starting state for A new? What we did is we took a random walk from the starting state of A old in the zero frequency graph. So basically, the terminal equivalence class that we get to, the distribution on terminal equivalence classes that we start at is statistically close to the distribution of terminal equivalence classes we would get by taking a long sequence of zero frequency streams.
How did you ensure that this walk is long enough so that you're close to the stationary distribution? I mean, how long?
How long do you need it? I mean, you can just get some finite bound, which is enough. So this is where the stream length gets really long. Yeah.
Right, but this graph is directed, so this mixing time could be exponential.
Oh, it's worse than exponential. Yeah. I mean, well, okay, yeah. It's not a small number of. It's not a small stream. It's just some finite bound. Yeah.
Okay, so exponential length here is acceptable.
Yeah, so what we're saying, because note that the streaming algorithm, the state space doesn't depend on the length of the stream, right? It depends on this underlying dimension n of the vector.
So the algorithm can depend, for example, if the algorithm has some kind of counter, how many elements it has seen already, then sort of its space state will depend.
So what we're doing is we're only counting states for which an x in the in this bounded integer box could reach. So basically, if I'm just counting a lot of things, so I'm just storing the first coordinate, and the first coordinate is increasing arbitrarily, I don't count states for the old algorithm once this count has exceeded m. And I design a new linear sketch where the number of states measured the same way is about the same as the old automaton's number of states. And now, if you wanted to sort of measure all possible states you could get with a new linear sketch, I'm claiming you could just take each of the coordinates mod poly n, and then you'll never blow up in this way. Because if at the end you're promised that you're inside of this small integer box, then you'll get the same answer if you take everything mod poly n, right? So, I mean, we don't want sort of lower bounds that come for trivial reasons, right? I just, somehow the state depends on, the space depends on the stream length, and we just make the stream length long enough. Okay, so what I didn't describe, so basically, what I'm saying is if I take sigma prime and I execute a long sequence of zero frequency streams, then this is like taking a random walk in the zero frequency graph, and that's exactly how we chose our initial state of the new automaton. We took a terminal equivalence class that you reach via random walk. then what you do is you update by sigma 1. You take a long sequence of 0 frequency streams. You get to another terminal equivalence class, etc. So basically, what you can show is in sigma prime, at the end, you're going to reach the same terminal equivalence class as you would if you were to execute. So you execute the old automaton on sigma prime. You reach some terminal equivalence class. And that distribution on terminal equivalence classes that you reach is very close to the distribution that you would get on states of A nu if you were to execute pi, a stream drawn from pi. OK, and sort of the key idea here is that at the end, you get to some terminal equivalence class, and you execute a long sequence of 0 frequency streams. That's taking a random walk inside of the terminal equivalence class. And so that random walk is statistically close. Where you land is statistically close to a sample from the stationary distribution. And the output of a sample from the stationary distribution is exactly what the output of the new automaton is. So does it make sense? It's sort of like the trick is to relate this one distribution pi to a distribution pi prime, where we take long sequences of 0 frequency paths, and we argue that this gives us something which is statistically close to the stationary distribution inside of each terminal equivalence class. Yeah?
Is there any reason why pi can't be deterministically one particular stream?
Yeah, so pi could be a singleton. Could be pi is just puts all of its mass on a single stream.
Right. Or okay. So I guess it seems like you can just make this argument that pi is singleton, right? Rather than okay, maybe I guess it doesn't matter.
Oh, sorry. I guess we're running way over time. Okay, so that's sort of the main trick. And basically, so what you can show is for every distribution pi, there is a new automaton that's generated via a reduction, which is correct with good probability on streams drawn from pi. You can show the way that we created this new automaton, it's path independent. You can get a randomized algorithm now that you have a correct algorithm for all distributions. And you can reduce the number of random strings you have in your algorithm by standard techniques. So similar to Newman's theorem, basically, if each randomness in your algorithm is correct for a constant fraction of your inputs in the integer box, then if I take, how many inputs do I have in my integer box? I have m to the n. And if each randomness is correct for a constant fraction of them, then my turn-off bounds, if I choose n log m such randomnesses, then they'll be correct. And so basically, I can reduce my number of random strings to something small. And the number of random strings is exactly the number of linear sketches that you get in the hardwiring. OK, so I don't have time to talk about the second part. Basically, this part is somewhat easier in the sense that once you know that you're path independent, you can define M to be a free module, which is sort of all of the vectors x which go to the same state as 0. So basically, now that each vector x only goes to a unique state, you can do that. You can show that the states of the automaton are the cosets of this quotient module. And using some lattice theory, the Smith normal form, you can show that the states can be represented as AX, where you take each coordinate mod a different value QI. And then there's some tricks to reduce this to get a sketch over the integers, which I won't talk about. So just to conclude, so one application of this is to proving lower bounds. As I said, it gives simpler proofs of existing lower bounds. And also, if the optimal algorithm is a linear sketch, then you just need to prove that there's no good linear sketch for your problem, which is an easier task than necessarily going through communication complexity. And this has led to some new lower bounds. Another thing is that there are many dimension lower bounds known for sketching various norms over the reals. Like if I want to sketch some matrix norm, via linear measurements, there are lower bounds for that. And the question is if you can use this framework to translate those lower bounds to get lower bounds in the streaming model. And there's a little bit of an issue there, which is that the lower bounds assume continuous distributions over the reals. And it's not clear if you can get those in this sort of finite precision case. So that's all. Thanks.
Questions? Or so David will be around tomorrow. So if you want to meet offline and ask more questions. Thank you.